Finally, I want to talk about mixed quantifiers. So that's when we have a propositional function of more than one variable. So here's an example of a propositional function of more than one variable. It says what? 2x plus 3y is greater than or equal to 5. So I've got a variable x and a variable y. By the way, in my propositional function, variables are called free variables because they're free to roam. And then if I put a quantifier in front of them, they're called bound variables. All right, so anyway, here's my propositional function. I'm going to put, since I have two variables, I'm going to have two quantifiers if I want. So I choose the universal quantifier both times. So this says for every x, for every y, 2x plus 3y is greater than or equal to 5. And I've chosen as my domain of discourse the set of real numbers. The question is that true or false? Well, since I've used the universal quantifier both times, for every x and for every y, then for this to be true, it's got to work for any value of x and any value of y I choose from the domain of discourse. Now, just because x is named differently than y does not mean that it can't be the same number. All right? All it means is it doesn't have to be that number. Well, probably isn't hard to see that this statement is false. All I need is one example, and I just pick let x equal y equal 0. Because when that's the case, I would get what? 0 is greater than or equal to 5. That's not true. There's my counterexample, right? And that is a rigorous proof. All right. Now, let's use the same propositional function of two variables, but now I'm going to use the existential quantifier both times. So there exists an x, and there exists a y, such that 2x plus 3y is greater than or equal to 5. My domain of discourse is going to be the set of real numbers again. So the question is this statement true or false? If I've quantified each variable, it turns my propositional function into a proposition, right? Well, I'm going to claim that this statement is true since I've used the existential quantifier both times. All I need to find is one example that makes this true. And the example I pick is let x be 3 and y be 0. In which case I would get what, 6 on this side, 5 on the other. 6 is certainly greater than or equal to 5. That would do it. Now life gets a lot trickier when one is a universal quantifier and the other is an existential quantifier. So let's look at this kind of example. What does this statement really say? I'm using the same propositional function of two variables again. What it says is, for every x, or if you like, for each x, there exists a y such that 2x plus 3y is greater than or equal to 5. All right, so kind of read it slowly and think about it. Is it true that for each x, there's a y such that 2x plus 3y is greater than or equal to 5? I'm thinking so. Now that y, since the existential quantifier comes second, is allowed to depend on that x. All right, so I think I'm always going to be able to find a y. But now I need to write it rigorously. All right, so this says for each x, I can find a y, right? I can't just say, like I did up here, let x be 3 and y be 0. Because I have to show that for any x you happen to pick, I could find a y. All right, so my argument starts out with, well, choose any x you want. Choose any real number x. I need to find a y that makes that statement true. Now that y has to be a real number. Well, after I've done a little work, side work, I kind of realized that if I let y be 5 minus 2x over 3, how did I get that? Well, I actually took the equation 2x plus 3y equals 5, and I solved for y. 3y is 5 minus 2x, and y is 5 minus 2x divided by 3. So really, anytime y is bigger than this, what I want to be true is. But since this is equal, I could just take y to be equal to that number. All right, so I'm going to say, for this arbitrary x, let y be 5 minus 2x divided by 3. Then it's not hard to see that if I plug that in for y here, I get what? 2x plus 3 times 5 minus 2x divided by 3. When I clean things up, 2x goes away, and I end up with 5, and it's true. 5 is greater than or equal to 5. So for any x, I have found a y that works. Hence, this statement is true, and that's a rigorous argument. All right, finally, let's switch the role of the existential and the universal quantifier. So let's say there exists an x such that for every y, 2x plus 3y is greater than or equal to 5. See the difference? This says I can find an x beforehand, not allowed to depend on y, that works for every y. That's what this statement says. Now, I claim this statement is false. That there's no way you can find an x that works for every y. Okay, now how can I write a rigorous argument, though, to show that this is false? Well, I say pick any x you want, choose any real number x. I need to show that that x cannot possibly work for every value of y. So the way I could show that is I have to show you that it fails for at least one value of y. What value of y am I going to pick? Well, I do the same kind of trick I do up here, except I want my y to work out to where this is not greater than or equal to 5, right? There's lots of examples, but the one I choose is let y be 4 minus 2x divided by 3. Then, when I plug it into this equation, do you see I get 2x plus 3 times 4 minus 2x divided by 3. 3's cancel. Minus 2x goes away, and that's how I end up with 4. And I know 4 is not greater than or equal to 5, right? So for any value of x you'd like to think works, I just shown you that it doesn't. I could find at least one y that makes it false. That's enough to show this statement is false. All right, now I'm going to let that sink in, and I'm going to stop for now.